And I'll just say ahead of time, I am not announcing all the co-authors of all these talks, just the presenting author. For the next talk will be Ralph Yeoman, Mapping Vesta, a Geological Overview.
Take this one. Okay, I just want to give you a summary what we did for the geology. So there will be much more detail in upcoming talks, but this is really to summarize what we think we know about Vesta after 3 months of work. The first is, what did we expect? We expected some kind of a differentiated silicate-bearing body. And that means we really think about to have impacts and a lot of impact erosion, ejecta deposition, material redistribution by gravity, and impact melt. We expect tectonics, maybe related to impact, of course related to impact, but maybe related to differentiation or volcanic processes. And we also expect from the theory volcanism, which basically means some kind of magmatic intrusions or surface flows. That's the topography of Vesta, and what you can see is we have a real surface where we have some younger craters which are named here. These are the major names of the quadrangles we have. We also have highlands, and we have some kind of depressions which are really look eroded. The most important thing here is then when we start to compare the relation between the radius and the topography, we end up with something like 15%. If we look at the Moon and Mars, we end up with something like 1% of topography of radius. So this makes Vesta a very hilly and very slope-intensive environment. And now look at the craters. We have a lot of different craters, crater shapes, but also different crater preservation. So that means we have relatively fresh craters with sharp rims, where we clearly can see the ejecta, and where we really can see that the ejecta is covering other features. I will come to this in a few moments. Then we also have craters which are a bit more degraded, but we still can see ejecta for these craters, and we have craters which are really heavily degraded, and we still see ejecta on this crater. So that means ejecta is, or distribution of material on Vesta is a major process. And we also have what we call ruined craters. That means features which are highly degraded and where you really can imagine that there had been an impact structure. Then we started at one region. That's a bigger crater in its southern region. And we look at the ejecta, and we counted the craters on the ejecta, and what we came up was we see a few of these old craters, of these old ruined craters, and then we see it's not following, that's the lunar distribution, it's not following the lunar distribution, but it has a kick here, a kink which shows that we increase in the younger features, the fresher features. And if you look at this kink, it appears for this crater, it's a 30-kilometer crater here, it appears at about 2 kilometers. And if you look at what we estimated so far for the depth to diameter ratio, then we end up with something like a regolith for this 30-kilometer craters, regolith covering craters which are smaller than 2 kilometers in the order of about 100 to about a kilometer. So if we interpolate this to larger craters, we have to expect a lot of ejecta covering the original surface, and this ejecta has been cratered again and covering the ejecta itself, and so on and so on. So we have really to expect a very thick regolith layer on Vesta. And the next, what was really puzzling for us was the shape of the craters. If you look at the shape of these craters, they look all a little bit elliptic. And if we look closer to this, then we see that you are not able to really see that the crater is a circle. But the reason is not because they are elliptic because of the impact. If you look closer, then you see a lot of these craters have this V-shaped form, and I will come to this a little bit later, but that's common on Vesta. And we also see this features, which are, we see it partly on the moon, but it's really unique. You see, it's not easy to fit a circle into this, and you also see we have a sharp rim and we have a smooth rim on these craters. And it's one on the same crater, and there seems to be a degraded rim and a very sharp rim, and that was puzzling some time. And then we found one crater which really gives us some hints what happens here, and that means impacts on slopes. And we investigated this crater a little bit closely with the 3D information we have, and you see this crater is sitting here on a slope, and if you start to look at different regions, we see it's a very steep slope, and the upper part of the crater is relatively high, and the lower part of the crater is, that's about a difference of about 3,000 meters. So that's probably caused some kind of an increase of the slope in the upper part of this crater. And finally, we measured the slope, and the slopes are much higher than about 30 degrees. In this case, we are in the order of about 40 degrees. And what we really see here is we see the crater is on a slope, and slope failure produces slumping, and then we have landslide going down and overrun the lower part of this crater. Okay, then if we look at the South Polar region, we also see some kind of scarps, and these scarps, they really look, like scarps we see on Mars, and if we clearly look at this, we see there is something happened here, and it's very close to what we understand is slumping or landsliding. Material from this scarp is running down the hill here, and if you look to this a little bit closer, then we really can see that some kind what we know from Mars, from other Earth, from Earth, and from other bodies, also the Moon. That's classical landsliding. And if you look at a wider part of this one is this area here, and this one is an area on the other side. That's a mountain of the South Polar region, and this is the floor of the South Polar region. And can you see the floor of the South Polar region has a specific tectonic pattern, and if you look at these two areas, they have a tectonic pattern which is perpendicular to this, and if we look closer to this, then we see some mass moving has happened here, and if you look at the contacts, we really see that there are contacts, so this material here overlays the floor, and it's the same on the other side. You can clearly see the material here overlays the floor of the large impact basin. And if you look at this, we will see a lot of these scarps, and we see a lot of this processes happens. And one of the big questions was at the beginning, why don't we see a real crater rim for this large impact? And the reason may be that we see a lot of impact processes, a lot of slumping, landsliding, which is correlated with the impact, but probably also has some reasons for later processes produced by seismic activity, by impact, and so on. We will have another talk on this, and that's the next talk, and that will really talk about the South Polar structure, so I can go on. And we also looked at the tectonic features, and tectonic features are global, and tectonic features are in the equatorial region, that's the blue one, and they are really correspond with the impact in the South Polar region. And we have a second tectonic feature which is also global and which is set off by about 30 degrees. And if you look at the South Polar region, we really can identify two impact basins which overlay each other. And finally, if we look at the circles at the center of the circles of the tectonic features, we really find it located in this area, and it fits with the impacts we found in this area, and there will be much more information about this by Deborah Beskovsky in a talk later on. Okay, then the theory for volcanism states that we should see some volcanic features. We should see at least dikes, which are very small, surface flows, which are very small, and we also expect only very small deposits on the surface due to the low eruption rates, and we also don't expect too much of, let's say, pyroclastic materials because of the low volatile content. But that's the theory. And then we started to look, can we see anything on the surface which is related to volcanic features? And the first what we saw was this dark material here, and there are some features which are puzzling. We will hear more about this later on, but one of these features is a mountain or a hill, and if you look at this hill, we clearly see it's located in the area of tectonic destruction here, and it also shows dark material, but the dark material is not directly in the hill, it's coming out from impacts because it's heavily impacted here. And you also see some kind of tectonic pattern here, but it's not really clear what this hill means and what this impacts means. There's one theory, it can be a dike, and impacts hit the dike and really show fresher basaltic material here. Another feature is in a scarp, and if you look at this scarp, you see there's dark material coming out, so that's probably flows. It can also be impact melt. However, there are many impact craters which show dark material in their vicinity, and we have low impact velocities, so there is another theory which says that most of this material is coming from probably impactors which have carbonate materials in it. Okay, conclusions. Vesta surface is characterized by a diverse geology. We have impact craters, we have ejecta blanket, we have tectonics, we have dark material, and we have a lot of mass wasting. Impact craters on Vesta are ranging from fresh to highly degraded and have characteristics which we know from other asteroids, that's mostly slope impacts, and we also see what we see on Mars and Moon. That making Vesta some kind of transitional body between asteroids and planets. The primary crust is covered with a lot of regolith, which has been estimated to be as thick as 100 meters, but may end up with a few kilometers. And it's multi-layered, shows a lot of events, and there is a lot of accumulation of ejecta over ejecta. The topography of Vesta ranges from minus 22 kilometers to about 19 kilometers relative to an ellipsoidal shape. And as I told before, we have this specific radius to topography level, and this is also in between what we know from terrestrial planets and the Moon and as other smaller asteroids like Lutetia. This also says that we have some kind of a transitional body, and the surface of Vesta exhibits this many slopes, so almost all impact on slopes, and that induces slope failure and resurfacing by mass wasting, which is due to associated gravitational and seismic activity, and that makes it an important geologic process on Vesta. We can confirm that there is an impact in the South Polar region, as already proposed by Hubble Space Telescope images, and we also see there is a second impact. And you can see there is some topography ranging between the central mountain of this impact, the younger one. And we also see the tectonics, and we know that tectonics is related to some extent with these impacts in the South Polar region. And relative dark material of unknown origin is intermixed in the regolith. And that's a lot of this material. It's in hills, it's in craters, in different features on the surface. And at this point, we have a set of theories about this, but we cannot really answer what the material really is. And in contrast to the models and expectations, we don't see so far evidence for volcanic activity. This may be due to the fact that large-scale volcanic features doesn't exist on Vesta, what we expect, It can also be that the volcanic process was really very early, and most of this primary crust is covered by ejecta, so we need higher resolution in order to find out what's going on with the early crust and what's going on with the resolution. And in general, Vesta's geology is more like the Moon and rocky planets than other planets. And I thank you, and I also thank you, a lot of people who really made it feasible that we have this data and that we can work with this data.
So we have time for some questions, and I realized I cut Chris's time short by a minute, so if anyone has a burning question for Chris, you could ask it after Ralph's questions.
So Ralph, we were having a little discussion there about your landslides, and I'm curious, do you think that they are post-impact?
No. We don't know it, but we know the largest, they are mostly related to the impacts because the shaking and a process of collapsing. But we think that a few smaller ones may be also due to something later than a certain large impact, because smaller impacts on Vesta also induce seismic energy. There is an impact structure which is really excavating this material. There are a number of impact structures. So there is one, the material is going out in a race in this direction. But the question is, where the material coming from? And so it's not clear. It may be also that this impact, this impactor itself has been brought, the dark material, as carbonatic chondrites or something like this. And okay, but the question is, why do we see it in certain impacts and other not? Why and why do we see it on this kind of features? Because it's a very small impact. And why is it on this hill? And we have a lot of material coming out here at this hill, and there are other smaller impacts which also show this. So it's a question. The major question here is, what is the dark material made of? And so far we don't have the resolution in order to really come behind this, because all these dark features are very small scale.
Still have time for another question or two?
Question for Chris.
Question for Chris? Can you move to the last slide? To the last slide? Yeah, we have a... We could show the movie?
What are you looking for?
I just thought we could put the animation back.
Okay.
Okay, no more questions. We'll start changing the speaker. You're gifted a minute.
Oh, goody.
Okay, our next talk by Paul Schenk is a south polar structure on Vesta from dawn using geologic, topographic, and compositional mapping and planetary analogs to test origin models.
Well, I first want to thank the Dawn Participating Scientists Program, but also my colleagues for the excellent global mapping products that have been coming out at a very fast pace, and for the excellent scientific discourse that we've been having over these issues. And this talk will focus on the South Polar Basin and I guess the up arrows, cider? Right, okay. All right. Now, we knew about that there was a large structure at the South Pole from the Hubble Space Telescope images that were taken in the last century. And it showed a clear indentation at the South Pole and a peak there as well. And logically, they concluded that it was probably a large impact structure, but of course at these resolutions you couldn't really be sure what was going on. And one of the key Dawn objectives was to look at this South Polar structure and determine its origin and its geology and its age, and to assess its potential link to the HAD meteorites from which from which they came. Now, as you can see from the topographic perspective map shown here at 250 meters and the fact that we've got 70 meters global coverage now, we've made a small amount of progress on this issue. And the plan of the presentation is to just go over the general properties of this structure, highlight a few of the unusual and key features and aspects of it, and I'm not going to have time to go into all of them. But then finally to put the basin into the global context. Now you've seen this map already. This is something that Ralph just showed. It's a color-coded shaded relief topographic map at 250 meters resolution. And there, okay. This is the outline of the structure here. It's fairly circular, a little bit of distortion out here because this is a polar stereographic projection, so it's a little distorted. But it's basically a bowl-shaped structure with a large central complex in the middle of it. Ralph pointed to several of the rim slumps. This is a topographic map across the entire structure along this line here. You can see the deep shape. This is the central complex. This is the high-standing rim, and this is the highest part of the rim, actually. It's about 20 kilometers high. Other parts of it are not so high up in here. Ejecta is identified locally in this region. I'm going to talk about that briefly. But putting it all together, it's fairly clear that the morphologic properties confirm an impact origin for this structure. And this view is another variation on the global topography. This shows the entire southern hemisphere, as the other slide did as well. This is a simple shaded relief map without the color. So you can see the structure within it. And I've highlighted several, or the basic morphologic components of the basin, a couple of which I'm going to talk about today. You have the outer troughs here, which are clearly defined in the global topographic map as these arcuate structures here. Deborah's going to talk about those in a subsequent talk. There's an ejecta deposit out in this area here, which I'll talk about. Ralph talked about the rim slumps that are highlighted in this area here. There are several others. I'm not going to talk about that so much. There's this annular floor material which covers the entire basin. I'm going to highlight that. And the central complex is here. And then there's a second basin underneath it, which you can actually trace here. And I'm going to talk about that as well. The first thing I'll talk about is the arcuate floor structure. And this shows a quadrant of the basin. This is the central complex here. The rim is more or less right about here. You can see it's not very well defined in this particular slide. So this covers a large section of the basin. It's about, this is about half the radius, so it's about 250 kilometers from here to here. You notice the low crater density, but I also can clearly see the tectonic fabric, which is basically arcuate, sort of spirals off the central complex in this direction here. It's composed of linear and arcuate fault scarps and ridges. In other areas, these are not so spiral, they're more parallel or perpendicular to the rim, but in this area there's a very clear spiral pattern. The scarps suggest extensional faulting. The ridges suggest compressional folding. The fact that this pattern is pervasive across the entire floor of the basin suggests that's related to crater collapse during the impact formation, with some subsequent modification. Now, when we first saw this, it was very peculiar because we hadn't seen a spiral pattern on a crater floor before. It didn't make any sense. Why would you have this? But as we looked into planetary analogs, we began to see more evidence that this may actually not be so unusual. This is an Iktomi crater. It's the freshest crater in the Saturn system, a very, very young feature. You can see it's got this sinuous and complicated ridge pattern in it on the floor. And these are all slumps coming off the rim. It's about 50 kilometers across. And then there's King Crater. King Crater on the moon is unusual because it's on a relatively steep regional slope, and the impact melt has actually ponded in one side, the downside of the crater floor, leaving a large part of the crater floor exposed and not covered by impact melt. This is the rim terrace section here. It goes around like that. This is the central complex, the central peak of King. You can see this arcuate structures coming off the rim, and actually in the same curve pattern as we saw in Rhea Silvia. And this area is interesting because it looks like a crosshatch pattern of cross-cutting sets. This suggests that this kind of pattern is the consequence of either radial convergence during floor collapse, or it's a consequence of floor collapse under rapid rotation. And this is something that the next speaker is going to address in more detail using numerical modeling, or at least potential for numerical modeling of this. So we're looking closely at this phenomenon. Moving on to the ejecta deposit, this is part of the global mosaic. So the rim is here, and the center is down towards the floor. And this is the area where we see the best evidence for an ejecta deposit. Other areas, it's not so clear. But you can see, and from the distance from here to here is about 150 kilometers for scale. You can see the striated texture coming off. There's a couple of low-bait flows, which you can just make out here, or low-bait scarps, rather, which we interpret as flows. And then you see this transition from the relatively smooth texture, undulating texture here, to the more densely cratered terrains to the north. And we interpret that as either ballistic ejecta emplacement or possibly a flow of impact melt, or possibly both. And we're looking forward to the high-resolution images coming down starting next week to actually get a better understanding of this phenomenon. The age of the structure, as you've seen in the images, the crater is relatively lightly cratered itself, suggesting that it is relatively young. There have been counts by Simone Marchi, the LPI group, and the DLR group. And the fresh crater population suggests a retention age of on the order of a billion years or so, with associated uncertainties. And we interpret that generally to indicate the formation age of the basin being about 1 billion years or so. And we note in contrast to that the heavily cratered terrains that Ralph described have ages at least 3 billion and generally in the order of 3.8 to 3.9 billion years. So that Rhea Silvia is relatively young. We note in passing that no HED ages, meteorite ages, are as low as that. And I'll get into that in the final slide. This gives an overview of the structure, the features I've pointed out so far, the overall plan of the topographic rim, the central structure, the various slump features that we see, this pervasive tectonic fabric all across the floor, the ejecta deposit, and the fact that there are a second basin underlying this structure, and there's one over here as well. And that's what I'm going to talk about next, is the existence of additional basins on Vesta. This is, again, that topographic map just highlighting Rhea Silvia, the young basin that we see, and also the presence of this second basin, which came as a surprise. We were expecting one large structure, so when we saw two, we were quite happy because that gave us a lot more to look at. And you notice that the rim of Rhea Silvia is very depressed in this area, and that's consistent with there being a pre-existing depression in the area. The topography of the basin would reflect the pre-existing topography in that way. This second basin has a diameter of approximately 375 or so kilometers and a depth, apparent depth of between 5 and 10 kilometers, depending on what reference surface you use. And the surface texture is mostly hummocky floor material, and there is a scarp here. Ralph actually showed a scarp with dark material on it, and that's actually right here. It's actually part of that structure. Now, in addition to that, when we look at the northern and equatorial areas, we see additional evidence for old degraded basins in the topography. There's a nice one right here. It's actually been partially cut by the rim of Reyes Sylvia. These are these are simple cylindrical maps, so we're seeing the entire surface now. These are not the polar stereographic anymore. But there's a nice arcuate structure here, very clearly circular. There's this one, which I just pointed out to. The southern section has actually been cut by Reyes Sylvia, so that's why it looks slightly out of shape. And there's evidence for other basins as well. This is actually that second basin I just pointed out, in case you didn't believe me in the first slide. That clearly shows a nice circular structure there as well. So we have a population on Vesta of large impacts that have sculpted the surface and created a lot of damage to the terrains. And there's at least 4 of them that are larger than 150 kilometers. Others are suspected. Now, of course, the older the basin, the more degraded its appearance is going to be. It's going to have less well preserved. So the certainty of identification decreases as the age of the basin increases. So we suspect there are other ones, but they're harder to be sure of. So these are the ones that we're pretty confident of right now. So we expect to find more, especially as we finish the northern mapping here during the final phases of the orbital tour. And Reyes Sylvia is the youngest of these basins. Now, to review, I talked about the unusual spiral floor pattern, and the next speaker is going to talk a little bit about this. There's 2 hypotheses. One is that it's post-impact modification. The other is that it is part of the basin, I'm misspelling there again, basin floor collapse. And it's curious, it's interesting because it may be revealed to us because there's a lack of impact melt. And we call this the naked floor hypothesis, that we're seeing these structures because we don't have huge amounts of impact melt flooding the basin, so we can actually see what happens structurally to it without it being masked. These basins, especially the 2 in the South Pole, this one and this one, clearly reset Vesta's geology, especially in the southern hemisphere where the existing geology has been obliterated. Ejected deposits have been identified proximally to the rim, especially in this area, but we don't really see dramatic evidence for thick deposits equatorially. We would expect a thick deposit of 10 or 15 kilometers of ejected to wipe out the geologic record, and that doesn't seem to appear to have happened. The impact may be related to the formation of the troughs, and that's a subsequent speaker will be talking about that. Actually, we have at least 2 talks on that topic. And finally, we have the 4 large basins between 150 and 500 kilometers that have sculpted Vesta's geology. Reyes Sylvia is the youngest, and that age may be correlated with the dynamic age of the vestoids, and this also may be related to the spread of HED meteorite ages that we see, in that Reyes Sylvia may have launched the meteorites but may not have actually reset the ages of the meteorites themselves because the shock is not sufficient to reset the argon ages. So Reyes Sylvia may simply be sampling all these other basins and the meteorites and the rocks that they formed. Thank you.
Questions?
Do you have any estimate of what the mass loss has been through the impacts on Vesta?
We have not looked. I'm sorry. We have not looked at that specifically yet. We've made a very crude back-of-the-envelope attempt to calculate what the volume of excavation has been for Reyes Sylvia. And it came to be 10 to the 6th cubic kilometers or something like that, which is enough to launch the vestoids. But because we're not sure of the exact reference surface that the impact occurred on, the volume is going to be a little uncertain. We look towards the modelers to actually give us a better handle on that because they can make an impact into Vesta and launch material, and they can tell us how much they estimate the mass loss to be. So there'll actually have to be a synergy between our observations and their models to tell us what the volume of excavation and loss to space has been. I think I answered that question.
Other questions?
South basin is south. This large change the shape of Vesta. You derive basic Vesta shape with impact. Have you an exercise? What will be the morphology with respect to pre-basin shape? Different?
No, we have not attempted to do that, largely because I think we want to get the center of mass determined as well, so that we can determine what the shift has been, that sort of thing. The geophysical teams are working on that problem.
Yes.
Terrestrial example, spider crater in Australia, central Auckland, spiral patterns coming out. So these are interesting. Seems to be a
Right.
common process. Is that again considered to be maybe an extensional process?
I've looked at some of the literature on the terrestrial impact crater record as well, and there's a lot of tectonic disruption on the floor of the complex craters on the Earth as well. We don't see it so much on the Moon because it's all usually covered by impact melt, but it's generally thought to be due to the convergence of material as it comes up towards the central uplift and the basin floor rebounds. If you look at the model that Eric Asfog and his group did, and you look at the animation, it shows a clear parabolic depression, and then the floor actually comes up back towards the original surface, but not completely. So there's a lot of deformation that's going on there, and this may be the direct evidence of that deformation. We're definitely interested in mapping it and seeing what the mass flow has been, because you can interpret, because of the scarped faces and where they're oriented, you can determine where the mass movement is taking place, and that's something that several of us are working on. It's a very interesting case.
Thank you, Paul. All right. All right, our next talk is Geologic Signatures of the Mega Impact on Vesta by Asfog and Jutsi. The speaker will be Eric Asfog.
Good morning. There's a sweet spot to modeling asteroids, which is when you have enough data and not too much data. I think the Dawn team is surpassing our ability to model it, and so leaving the modelers in the dust. But I'm going to show some results from a paper that Martin and I published earlier this year, and some interpretations based on what we've now seen with Vesta. And how do I go forward? Yeah, go ahead. Thank you. So craters comparable to the asteroid or planet diameter reveal major aspects of a target's geophysics. This has been known for some time, that you can use these big holes to probe deep into the body, not just to see into it, but to understand how it responds to an event of that magnitude. So Fujiwara, Peter Thomas, many other papers looking at big craters that form on planets. And we've now got this appreciation that everything has one last biggest event. And then we study that to try to understand the interior. And likewise, the rheology of the interior and the surface failure in response to a collision can tell us about the layers or the kind of structures that are inside. So, for example, the McKinnon and Meloche model for multi-ring basin formation tries to understand the asthenosphere and crustal structures based on multi-ring structures. So Vesta has this bonus. It has two bonus features. One is rapidly rotating, and we can learn collision geometry relative to the original spin geometry. And it has this astronomical family of ejecta, the V-type asteroids. Next, please. So, for example, we can apply modeling tools. This is from Margarita Marinova's work in Nature and Icarus studying the hemispheric basin on Mars. Next. And the collision themes for Vesta, I'm going to stick to 3 themes. This is probably the most important, and I'm just going to kind of gloss over it because we don't know enough yet. But these are 2 interesting tractable themes. First of these, megacratering transforms asteroid interiors. Vesta's, as Ivanov just pointed out in his question, you know, the Vesta now is not the same as it was prior to this collision. And then likewise, the interior rheology controls the cratering process. So there's a feedback there. Vesta's megacraters grow and collapse on a timescale comparable to its 5-hour rotation, typo, and that leads to possible Coriolis effects that I'm going to discuss in a bit of detail. And lastly, related to that point, is that mega ejecta that falls back over 8 or 10 or 12-hour timescales, is expected to drape it in odd ways, and does it. Next, please. And so going back to some old studies, 2D models, back in the day, this was 15 years ago after the HST observations and some of the speckle observations revealed this big hole on the south pole of Vesta. 2D models are easy to analyze. I don't expect you to understand what all these, or read what all these labels are, but this is a 2D model. You just show a slice and that's it. When you get to understanding the importance of rheology, and you know that, for example, particles near the axis behave very differently from particles near the equator of your model, you got to be a little bit careful in 2D. And this can be tractable, but also the fact that most impacts occur at 45 degrees leads you to move to 3D models. And 3D models are required to capture the physics, all the physics, but it's expensive lower resolution. But time's gone by, and now we're able to do 3D models at about that same resolution as 15 years ago. And so what I'm going to show you are runs that took about 2 weeks on 32 processors. And the disadvantage of 3D isn't just that they take longer to run, they are much more challenging to analyze. You have to look at it from all different points of view, and it opens up a whole new parameter space. And so, for example, here's a mega cratering controlled by rheology. You can put in, this is work done, 10 years ago now, looking at asteroid Matilda, and if you make it a big pile of marbles, you can explain, for example, why Matilda doesn't have ejecta that are bound to the body, at least at the resolution that we could see from the near mission. And the idea here, if you can go to the next slide, is that the porosity created a situation where you launched ejecta faster than escape velocity. Anyway, whether this applies to Vesta or not is debatable. Vesta, we believe, is a consolidated body deep inside. It has a high density. But the properties of its outer 50 kilometers matters greatly, especially when the impactor under consideration is about 50 kilometers diameter. And so that's something where we're flirting at the edges of understanding how to model that. And then put that into comparison with the moon. 50 kilometers deep in Vesta has the same pressure, essentially, as the moon at 8 kilometers, so the structures might be comparable 50 kilometers deep. I just wanted to point out that there are ground truth data. This is crater Leo in the northern plains of Mars. It's about the same impact, comparable impact velocity, scale equivalent impact. And so we can study craters like Leo on Mars, perhaps, to understand better the cratering process. So the point here, for the last few minutes of my talk, I'm going to talk about the crater collapse in the non-inertial frame, rapidly rotating body. Growth and collapse occurs at about the time scale of the asteroid rotation. And so the question is there a geologic imprint? And I'll get to explaining what this picture is in a moment. And so Vesta has about 5 times Earth's angular velocity. The impact shock imparts a velocity field in one relatively instantaneous inertial frame. So you get a velocity field after the impact comes in. And then crater excavation occurs in one inertial frame, and crater collapse occurs in another inertial frame. And so here's the crater growing, and you can look at, for instance, this vector. Here we go. This vector here, and a quarter of a rotation later, here's the same material coming in, and it's coming in at a different angle, and that's the Coriolis effect, essentially. Next one. So here's a movie of the impact, and this is from our paper earlier this year with Mark Nuzzi and myself. And it took about a quarter of a Vesta's rotation for the rebound to occur. And during that quarter of a rotation, the vectors going out were different from the vectors coming in. And so you can ask, is this a stormy crater? Does it create a maelstrom of flow in the crater center? And there is some indication, as Paul Schenk just discussed, about the arcuate forms near the central region of Rhea Silvia. But if you do a Coriolis parameter study, so this is the rotation rate, this is the latitude, and the length scale of the motion of order the radius of Rhea Silvia, characteristic velocity, it's about 100 meters per second for most of the flow based on our model. And you get a rotation frequency of Vesta, and you plug all this in, and you get a Rossby number of order unity. What does that mean? Well, Rossby order of order unity means that Coriolis parameters start to dominate the flow. And this is comparable to the Rossby number of oceanic systems on Earth. So if these really are Coriolis rotations, then the impact must have been equatorial or mid-latitude. If it was up on the, if it was at the equator, this should have been. I guess the general point is that the location of the crater can, in principle, be deduced by a mapping of these striations. And next one. And so the second component of this is what happens to the distal ejecta. So this was the flowback of material, and the non-escaping ejecta, you can trace this as well. A time scale is comparable to the asteroid rotation. So the rotation spins underneath the ejecta and winds it up. And we predicted massive folded sheets about 10 kilometers thick with abrupt termini. And it's not clear that these are seen. Simone et al. In preparation don't really see obvious structures such as those that we predicted. And so we can ask these questions. Is the target structure different than modeled? Well, sure. Is the impact event less energetic than modeled? Probably, because based on the fact that we have two basins instead of one, each of those carries far less energy. And did we model the event to completion? And this is going to be my concluding point in a few minutes, is that we probably haven't modeled these to completion yet. Next slide. And so here's the excavation depth. Basically, purple means that you're seeing stuff that was dug up from 50 kilometers deep. Yellows from about 10 kilometers deep, and you drape it over the asteroid. It's a model. It's a movie of a model. We don't know whether this is really what happened to Vesta, but here's this prediction of these ridges. And this is what you had in that 3D view, where you had ejecta going out and then folding back on itself because the asteroid catches up to the ejecta. And so you get a triple overturned flap. This is a simulation of a nominal impactor, 50 kilometers diameter at 5 kilometers a second, striking a nominal Vesta. We have a granular flow model from Yopa et al. 2006, which we've implemented, which basically freezes up the material when it becomes based on an inertial number calculation. And we map a lunar-like regolith porosity to Vesta's pressure to give a structure for the outer material. And it's about 5 million particles. But you can see this ridge here. It's about 15 kilometers thick. Next one. And so here's the same impact hitting a non-rotating Vesta. Here's the same impact hitting a rotating Vesta, or a non-rotating Vesta at 45-degree angles. So this is a classic oblique incidence. And here's the same 45-degree incidence angle on a rotating Vesta. It leaves this big lobe of stuff that I don't think we see on Vesta. Next one. And so this is the provenance map of the same, seeing different angles of where the goodies from down below are being dredged out all over the surface. Next one. And here's a cutaway view, and you can see the double overturned flap flapping back again. There's a triple flap. Next one. So no ridges? Well, what's wrong with the model? Well, one, the crater's smaller than modeled. I think this is true. We modeled too big of a crater. Vesta is stronger than modeled. This could be true. Lava flows may reconsolidate the regolith. Many of the HED meteorite suites are breccias and welded breccias, and so Vesta may have strength in its outer material, which would lead to higher ejection velocities and not this gravity regime crater. Next one. But my favorite is that just the impact wasn't finished yet, and this has been alluded to by a couple of the previous talks, where by the time this is done, 8,000 seconds have gone by, 2 hours have gone by, and Vesta may have a very high Q, a very high quality factor, so its attenuation in the deep interior, it may ring for hours. It may ring for days. Earth rings for days after a major earthquake. And so this ringing may actuate surface materials and soften some of these features to later time, as modeled by Richardson et al. Back in 2005. Next. And so to conclude, the South Pole Basin, Rio Silvio, is key to understanding the geology of Vesta. The arcuate patterns may give independent indication of the impact latitude, which would be very important for understanding how it has evolved subsequently in time. And the family of asteroids might provide the best constraints for next generation hydrocode simulations. We've opened a can of worms with these kind of 3D models. Now you're sort of wondering what the heck to do, because it takes to go to kind of the next step to systematically model all the kinds of impacts that could be suffered by Vesta. You better be prepared to build a massive machine and run it for a couple of years, nonstop, just doing Vesta. And so I think 3D is best used right now as a tool to test a few key hypotheses, modeling carefully to later time. Thank you very much.
Any questions for Eric?
I was wondering how the calculations would be affected if you didn't have that big iron core. Would you get a similar outcome, or would it depend on the size of the core?
You know, it's an interesting question. In the 2D models, we put in an iron core, basically built it as a terrestrial analog, and a lot of the seismic energy gets trapped in the core. It kind of is like Jeff Moore called it a roach motel. The energy gets in but can't get out. I'm not sure whether that's just a curiosity or whether it strongly influences post-modification.
Other questions? I was curious if your models had any predictions for these kind of large grooves and fractures seen also that might be related to the impacts.
Well, that was the scary question. I mean, you can make, I think that's going to be the next key, because the flowback in this granular model, we didn't get ridges. You know, we just got sort of continuum flow. The rheology in our model is quite simple, and I think actually if you have structural integrity in the surface, you know, there's a lot there to learn, the spacing of the grooves. I'm looking forward actually to Deborah's talk, because I want to understand a bit more about this. But this is, you know, in some sense, I would view Vesta's South Pole Basin as a big multi-ring basin, and these are the rings of the basin structure. And so I'd revert to older models of multi-ring basin formation to say what those are about. But I think on a curved surface instead of a flat surface, the geometry is going to be quite a bit different.
When you look at your model, can you actually take snapshots of the shape of Vesta as the impact is evolving to see whether it's deforming, and then we can look at what the stresses are in various regions? Is that possible?
Yeah, there is stress associated with every point at every time, so we could do sort of a map, you know, of the stress condition and of the strain that's occurred at different regions, and we just haven't done that yet. Yeah. Thank you.
All right, the next talk is Structural Features on 4 Vesta Observations and Analysis by Buchkowski and 25 co-authors. The talk will be given by Deborah.
Hi, everybody. Everybody else who spoke is much taller than me, so let's move this down. Can you go forward? Oh, do I? Okay. So as we've been seeing all morning, images of 4 Vesta have been successfully acquired by the framing camera. They're beautiful images, aren't they? And what became instantly obvious is that these reveal the presence of both large-scale and small-scale structural features on the surface of the asteroid. Now, you might have noticed in some of the earlier talks, especially Chris and Ralph's, there's this sense of looking at Vesta and trying to figure out, you know, it's this intermediate body. It's got some similarities to the larger planets that make it a little different from the other asteroids. So if it is a more planet-like body, could Vesta have been subjected to planet-like tectonic processes? On other asteroids, when we observe tectonic features, for the most part, they've been tied back to impact formation. During impact features, you get these other structural fractures. But could Vesta have formed some of these features due to more planet-like processes? So let's start with the large-scale structural features. These include an equatorial set of troughs, which we've already heard discussed a lot. There's also a trough extending at an angle from the northwest from the equatorial troughs. It's another large giant trough, but it's at a different orientation. There's the grooves and ridges on the floor of the Rhea Silvia Basin, and then there's these steep scarps that are bounding the regions of high elevation terrain. So obviously the analysis of these structures will contribute to our knowledge of the stress history of Vesta. To do this analysis, I was using a tool developed at APL, where I work, called the Small Body Mapping Tool, which utilizes the Vesta shape model. And we can drape the framing camera images over the shape model, and then when we outline where each of these structures are, it has a topographic component because it was mapped right onto the shape model. So as I look at a fracture that's going around the asteroid, especially the super long ones, we can actually use the topography to model a plane that cuts through the asteroid. And this way we can try and get a sort of strike and dip of the fault. When we have planes, best way to determine if the planes are related to each other is to look at the poles of the plane, the 90-degree point coming out of that plane. Because if the poles cluster, then these planes are similarly oriented. And structures that are similarly oriented are likely to share a common formation mechanism. So the equatorial troughs. These are linear structures that encircle the asteroid. They're roughly aligned with the equator. For the most part, these are wide, flat floor troughs bounded by steep scarps. They surround the asteroid for almost 240 degrees of longitude. They cover most of Vesta. There are also some muted troughs and grooves and pit crater chains in the third of Vesta that is not covered by these larger troughs. Lengths vary from 19 kilometers up to as much as 380 kilometers, and widths can be up to 15 kilometers. And currently, we've got about 86 linear structures at that orientation. So our analysis indicates that these are coplanar. The poles do cluster. They cluster at around 78 degrees latitude, plus or minus 10 degrees. The longitudes do vary. They do not all cluster at the same longitude, but given their location on the asteroid, the longitudes are actually really close together. So even though they're different longitudes, it's actually a very tight cluster, pretty much on Rhea Silvia's central mound. Then there's the northern trough, and you can see it really clearly right up here. And there's some associated features down below. This appears to be an older trough. It's got shallower walls, rounded edges, it's infilled, there's heavy cratering. It just really looks older. It is 390 kilometers long, it's 38 kilometers wide, this one's huge. And then the other features associated with these smaller features kind of in here range from about 31 to 212 kilometers long. There's only about 7 features that we've associated in this set so far, but the analysis does indicate that they are coplanar, and more to the point, the pole clusters at 60 degrees latitude, plus or minus 10, and at about 160 degrees longitude. Well, what does this mean? Why do we care? What's interesting is that the orientation of both of these sets is consistent with models of formation due to giant impact. Now, these are models that were originally designed for smaller asteroids. They might not necessarily, the models that I was using when I was originally doing this work were actually developed for IDA. IDA does not have a core, so they probably don't apply to Vesta, but there will be later models in the next talk that might explain how these things could have formed due to impact. But just to show you where our analysis has led us, the 2 basins in the south of Vesta have centers at 70.4 degrees south for Rhea Silvia and about 50 degrees south for the older basin. And here in red are where the poles cluster for these 2 sets of fractures. And interestingly, that older northern trough corresponds to the center of this older basin. So we seem here to have these large-scale structures on Vesta, but once again, they're tied to an impact. So let's look at those southern structures. These have been discussed by Paul and by Eric, so they've already been gone into in some detail. And we've already seen that many of these structures might simply be due to impact on a rapidly rotating body, or even when you start looking at some of these grooves and troughs on the floor, they actually seem to perhaps just be flow faces for mass movement on the basement floor. So once again, we have fractures and things that look like structures, but they seem to be due to an impact process. So we're still looking for signs of internal tectonic processes. Well, let's look at some of the smaller scale structural features. Features that we've been able to observe on Vesta include pit crater chains. And here's a pit crater chain right in here. And if you look, many of these circular features in this chain, it's a chain of merged pits. And these pits have no rims and show sign of collapse. These are not impact craters, they are pits. And you can see there's some fault faces down here that are bounding the pits. Pit crater chains are modeled to be formed when you have loose material covering a tectonic fracture, a graben or a fracture set. So what you would see here is that loose material kind of filtering down into the underlying fracture. So further analysis, things that we're going to do with these pit crater chains now that we found them, is a study of the pit depth. And then we can determine how much regolith or loose material has been drained. And if you want to see some of these features closer up, you can go to the poster tomorrow for the AV9 quad by Wyrick et al. Other small-scale features include possible thrust structures. We have steep faces backed by long, shallow slopes, which resemble the surface expression of buried thrust faults on other bodies. So we need to complete an analysis of the height versus length and then the relative slopes to determine whether or not these are in fact buried thrust fractures, or buried thrusts, excuse me. And then we can compare these to models of wrinkle ridge formation from the Moon and Mars. And to see these features in more detail, go see the poster by Scully et al. On AV4, the Demetia quad. And then another small-scale structure, Ralph was talking about these earlier, are possible dikes. Here's one. He showed you a lovely, one of these linear hills associated with dark or unusual color deposits. Here's another feature that has been under discussion as a potential dike. It's a long, dark, linear feature. When looking for potential dikes on Vesta, we're still looking for unambiguous evidence of lava intrusion. So these evaluation of these smaller features is still ongoing. We're getting better and better resolution data all the time, and it's actually a fairly decent-sized body. So we're still finding new features. We're still trying to verify the identifications, especially of the thrust structures and the dikes. And once we have verified these identifications, then we can deduce potential formation mechanisms and determine causal stress fields. And then we can ascertain how that these relate to the larger Vesta stress history. So just in summary, this is not a conclusion, because this is a work in progress, but in summary, right now, Vesta covered by both large and small-scale structural features. The large-scale features appear to be related to the formation of Rhea Silvia and the older southern basin, but these smaller features may be due to internal tectonic processes, although more detailed analysis needs to be performed before we can say for certain. And it's these smaller features that might indicate how Vesta is tectonically active in a planet-like manner. Thank you.
Okay, we have time for some questions. Okay, we have a question over here.
Carol Raymond's talk, unfortunately, is after mine. But what's interesting about Vesta, and I believe Chris already touched on this and Ralph touched on this, so it's not a huge surprise or a spoiler if I mention this, is Vesta is differentiated. It has a core, it has a mantle, it has a planet-like interior structure. So it is not out of the realm of possibility. This is not just a chunk of rock floating in space, but this is a little mini planet, and so finding planet-like stresses and strains and interior processes that could result in features on the surface is entirely possible, and so we should be looking for these features.
Thank you, Deborah. Okay, the next talk is the Tectonics of Vesta, Indication of Spin Up and Reorientation by Schmidt. The talk will be given by Brittany Schmidt. And do you want to drive or? Sure.
Alrighty, so forgive me if I'm a little rusty. I'm on the Dawn team as part of the EPO outreach. So all of the work that I'm showing you today is stuff that was completed and published in my thesis in May of 2010. If you're interested in that, because of my other postdoc position, I haven't been as good about getting this out. It's in the process of getting out in Icarus, so we're not quite there yet. But I'm excited to talk to you about the stuff that I worked on here for Vesta. And really, all of the data that I'm talking about is pre-Dawn for the most part. These are based on the shape model from Peter Thomas's work from Hubble Space Telescope. And so that's what I'm showing here. And what you noticed in the shape model from Peter Thomas was, of course, the detection of this giant south polar impact structure, a prominent equatorial bulge, some of these other features that could be basins, but we weren't quite sure at that time. And so Dawn is giving us a new perspective on that story. And so I'm going to tell you about the work that I did leading up to that as a PhD student with Chris Russell. And so really the motivation for my talk was to try to understand what Vesta was like at the time of the impact. It's an extremely fast rotator. Might that be part of the story? In addition, we have a debate about the origin and the dates of the HED meteorites. Are they from Vesta? Are they from Vestoids? Have they been secondarily lifted off the surface? And so in the process of compiling that work, if you look at the work from the Vestoids, there's a really good review paper by David Nesvorny in 2008 that basically talks about the need for the family to be at least 1 billion years old. However, there's a distinct population that spreads into the inner solar system and includes the near-Earth V-type asteroids, and that has an indication of an age around 4 billion years ago. And so the second is that the cumulate unbrecciated eucrites, the cumulate unbrecciated eucrites have impact ages of something around 4.5 billion years ago. And so how is it possible that this impact happened early in Vesta's geologic history such that there might be a geophysical indication of that process on the surface, and how did it impact the body as it continued to evolve? Observations that we had to explain was this large impact crater, 460 kilometers in diameter, centered near the South Pole. This should say near the South Pole. And the fact that despite that feature, Vesta is actually, its equatorial bulge is fairly symmetric about its rotation axis. So it's at least potentially either the impact happened at the South Pole or it's tried to erase the impact, and so it might have been warm at the time of that impact since it seems to be close to relaxing about its current spin axis. That's clearly not completely the case. So the idea here was that Vesta may have reoriented so that its final shape and rotation state is controlled by the initial impact latitude, the thermal state of the object at the time of the impact, and the initial internal structure. And so this is kind of a diagram of how that process works. On these protoplanets, Pallas, Ceres, Vesta, the large dominant features we know are impact basins, and they have an incredible potential to change the rotational state of the body. So if you actually create a negative load by inducing this impact, you liberate material from the surface, it can change the rotational state because it wants to put negative loads, at the poles, much like we see in Enceladus, and wants to put positive loads, huge equatorial bulges, right around the equator. And so, if, for instance, this impact happens at a mid to equatorial latitude, then the desire is for the body to reorient and put that basin at the pole. And so, another example of this that we're all probably familiar with is the idea that this process has happened on Enceladus. Enceladus is a slow rotator, so that's part of the story there. But you have this large negative anomaly at the South Pole. So how do we model that? We're interested in the coupling between the rotation and the deformation. Classically, a lot of work has been done solving the elastic solution, where you assume that the viscous component, the viscous impact from the mantle has relaxed by the time the body's done deforming. Instead, here we look at the impact that the surface load has on the moment of inertia, and it induces a normal stress. You allow the body to deform viscously and viscoelastically towards an equatorial shape for a new rotational potential as it rotates. So we're looking at the coupling of rotation and shape deformation. That couples into the thermal evolution because its ability to do so depends on the rigidity of the mantle. And so we have this coupling between these two forces, between the stress and deformation and the rotation. What might the surface implications of that be? So we start with the body initially relaxed about a rotation axis, solve partial differentials in time for the position of the surface and its rotation axis. We induce an impact at a given latitude. We just basically model a cylindrical cap. We solve then for a perturbation to the shape, to the moments of inertia, and to the rotation state. We allow the body to deform as it rotates towards that new potential, and then you get the feedback between them. And so eventually we get rinse and repeat until we get an equilibrium solution for its rotation state. So here is basically just plots showing that this is actually important. On the left here, you basically have how it's deforming if it's, I'm sorry, I can't quite see it. Sorry about that. So the dashed is this rigid case. So if the body can't deform, do you see it actually deform in time, and how long does it take for that reorientation to occur? And on the other side, if the body is completely viscous, what happens as the body is allowed to reorient? So we really do see a coupling between the rotation state and the viscosity of the mantle. So I'm going to show you some model tectonic maps. In these cases, blue is extension, red is compression, and white here is shear. So these are all surface strains. This black line, all of them are with the impact at the North Pole. It doesn't really matter. We're in the inertial frame. So this is just where the impact, the crater rim is. And then there's a green dot, which initiates the center, the initial pole orientation for the body. So I'm going to show you a slowly rotating case. And so as you see, for the slowly rotating and just viscous case, you allow the body to completely relax and erase the impactor's the initial impact. And so you get a pattern of tectonics that is unique to each particular case. So this is for a relatively warm Vesta, something comparable to the Earth's mantle. And then on the right now, we're looking at a much more rigid case where really the pattern doesn't seem to change very much. But the lesson to take home is that the difference between this pattern and this pattern is really noticeable, and therefore you might actually be able to use the geophysics, the surface tectonics, to tell you about the timing of that impact. However, here's a comparison, all for this fairly rigid case where the impact is first at 75 degrees, an impact at 45, and an impact at 15. And this is more of the elastic solution where you allow the body to just completely reorient, and this is for a slow rotating case. So this is the viscoelastic case as you allow the body to reorient when it's slow rotating. It turns out that for Vesta the case is a little bit more complicated than that. I'll just highlight here that you'd be able to see the tectonic differences between these two cases. But on Vesta, we have a problem, and it's because the degree 2 shape of Vesta, that equatorial bulge, is huge. It's absolutely gigantic, and really no impact crater can reorient it because of that. It's incredibly rotationally stable. So either this impact happened at the South Pole, or it happened when Vesta was rotating more slowly and has had an impact since then. And so the cases that we considered is that you really can't do this completely viscously. It needs to be a viscoelastic solution where the mantle can deform, but you still have a crustal signature of that impact, so that this initial disruption really removes a significant portion of the crust, shatters that material, and so we're talking about probably a cooler Vesta at the time, but still the potential for some activity. And as I'll show you is that it really requires spin up for any of these reorientation scenarios to occur. So here's some more plots. What I'm showing here is in the blue is an impact at 15 degrees, and the red is an impact at 45 degrees south.